Hi everyone. I welcome you all in the seventh lecture of COMSOL Simulation. So in today's lecture, we are going to understand, the calculation of pressure drop as well as velocity profile while using the COMSOL software. And here we'll study only for the laminar flow for the Newtonian fluid in the circular pipe. And in the next lecture, we'll see for the non-Newtonian flow. So to understand these things, first we should know what are the Newtonian fluids. So when we talk about the Newtonian fluid, the governing equation is like say Newton's law of viscosity, which is tau that is equals to mu into gamma dot, where tau is called as the shear stress and gamma is called as the shear rate, that is del u by del y, and mu is the viscosity. So if we plot the shear stress versus shear rate, where shear stress is on the y-axis and shear rate is on the x-axis, so the slope of this line that gives you this viscosity, and that is a linear profile. And when we calculate the velocity profile inside the circular pipe for Newtonian fluid, so let's say if there is an inlet pressure P in and outlet pressure is P out, but in COMSOL basically it calculates with respect to the atmospheric pressure, so the gauge pressure at the outlet will be zero. And in COMSOL, we will be solving, two equations simultaneously for Newtonian fluid. That is a continuity equation, which is del dot U equals to zero. And then there is a Navier-Stokes equation that comes from, balancing the force for a particular fluid element in the inside the circular pipe. And that is rho into del U by del T plus U dot del into U. That is equals to minus del P plus mu del 2U plus rho G. So this is basically force, mass into acceleration term in the left hand side, and right hand side there will be pressure force, shear force, and the gravity force. And this basically gives you the velocity profile. And once you solve both of these equations, this gives you a velocity and as well as the pressure drop calculation in this pipe. But analytical solution for Newtonian fluid is also there, and we can drive the analytical solution while doing the force balance inside the circular pipe. But here directly I have written the analytical solution for pressure drop, that is equals to 32 mu u L by d square, where u is the average velocity of the fluid inside the circular pipe. So whenever we want to calculate the velocity, and we'll also see that whenever you assume that inlet velocity, that should be the average velocity of the fluid inside the circular pipe, and you would be knowing the formula that u average equals to u max by 2, or maximum velocity you will observe at the center, and that will be equals to 2 into the average velocity. Okay, so we'll solve using COMSOL. So let's try to understand how we can solve these things. So first I'll open the COMSOL software. Obviously it will take some time because this software is bit heavy. Just 1 second. I should have opened these things earlier only. But in today's lecture, only we will solve for the Newtonian fluid. And analytically also, you can validate the pressure that you are getting using the analytical solution. You can also use this for calculation of the pressure drop uh, using the analytical formula, and the results that you will be getting from the COMSOL simulation. You can validate both of these things. For second thing is that in circular pipe, you would have studied that velocity profile, that is UR, that is equals to U max into 1 minus R square by capital R square, where small r is the radial distance from the axis of the circular pipe, and capital R is the radius. So at every location of R, you can substitute the value and you can calculate the velocity profile analytically, and then you can validate that results with the result that you will get from the COMSOL. And as I've told you, for Newtonian fluid, you will be getting a parabolic velocity profile because u r equals to u max into 1 minus r square by r square. So it's taking some time. So let's see. So yeah, so here you can see that in this you will be getting a velocity profile that is circular. Sorry, parabolic velocity profile. Uh, Yeah. So now, okay, so now you can see we have opened the console. So you must be knowing this user interface that already I have described in my previous lecture. So now what we will do here, So we'll go to the model wizard and we'll go to the 3D because our circular pipe will be 3D. So we'll create a 3D geometry and then we'll go to the fluid flow, then single phase flow, and then we'll go to the laminar flow condition because we are going to study the thing in laminar flow. And then once it is getting added, you have already added the physics that is the laminar flow. Then we'll go to the study and we'll go to the stationary. Once we go to stationary, then we will do done. So after doing these things, first, before creating the geometry, I'll go to the parameters, global parameter, and we'll define the length of the pipe. So let's say I'll define 0.5 and meter. So we have to place a big bracket and then we place the unit. Once you do these things, the value will come appear as 0.5 meter, right? And here I'll write length of pipe, right? Then we will put diameter. Let's say I'll put diameter is 0.1 meter. And now you can see that is a dia. Then let's say we'll substitute the average velocity, inlet average velocity, and I'm just substituting, let's say 0.01 meter per second. Once you substitute, you can get see here we are getting 0.01 meter per second, and that is average inlet velocity of fluid inside the circular pipe. Now, this has been done. Now, let's go to the geometry. So, the goal is to create the pipe. So, in order to create a pipe, you have to, import a cylindrical kind of geometry. So, once we do these things, okay, so now you can see here lots of things will come and how we create geometry in COMSOL already I have described in my previous lecture. So here I won't be describing all these things in the detail. So just I'll try to substitute the radius here. So radius will be diameter by 2 and D already I have defined and length I have already defined with L. And I'll try to use this position I mean x0, y0 and z0 that is the initial coordinate and once I'll build this you can see so this cylinder is getting created in xy plane and z is the axis of the cylinder. So along z direction, this is length and xy is the plane of the cylinder, something like that. Okay. So now what we will do, we have to define. So now we have defined length 0.5 meter of length. You can see 0.05 meter length of this cylinder and then diameter would be I think minus 0.05 to 0.05 so 0.1 and length is 0.5 sorry it length is 0 0.2 0.4 and 0.5 so now we have checked the geometry this is fine now we'll go to the materials so once we go to materials so here I'll add a recent material and I'll add water so how to add the materials if you have some you want to use some another materials already I have explained this in my previous lecture. So here the recent material that is there skin copper air water. So water is my recent material and I want to use water because I just want to understand how what is the velocity and pressure drop profile in inside this circular pipe for the water. So once I'll do this I'll add these things. So now you can see that the materials got added because this domain looks like blue and this is one. So material is being added now. Now I'll come to laminar flow. So in laminar flow at inlet condition, once at inlet condition, I'll select this domain because this will be my inlet and here I'll use velocity that we have defined is u naught. It was a small u naught. And then I'll go to laminar flow. Then I'll click right click and then at outlet we will define a gauge pressure and that will be zero. Okay, because this will be a gauge pressure and we have defined the inlet we have defined the outlet now we'll go to the wall and we'll define the no slip boundary conditions so lots of boundary conditions are there for the wall leaking wall when you want to create some kind of leaking blood vasculature kind of thing then you can use leaking wall slip velocity lacto osmotic velocity many boundary conditions are there for the wall but here we are going to use the no slip boundary condition so boundary condition has been added. So all of these things are there now. And then we'll come to the fluid property. And in fluid property, if you see here, there is a constitutive relationship, and that is Newtonian. So since we are, interested in solving the problem for Newtonian fluid, that's why we will click on Newtonian. If we want to go for non-Newtonian, then there is an option of inelastic non-Newtonian. But in my COMSOL model, it is showing only inelastic non-Newtonian. But if you are using some advanced version, then it can show some another non-Newtonian fluid as well. So right now we are interested in solving the problem for Newtonian fluid. So we'll use Newtonian. And then if you see the equation, this first equation is called as the Navier-Stokes equation that I have already described. But since we are going to study in a steady state condition, that's why time dependent part is zero, and only you can see that this acceleration mass into acceleration part into del dot pressure force plus viscous force plus F is gravity. So I mean another equation is continuity equation, and that K here you can see that is mu del U plus del U whole transpose. So that is the viscous force. I'll explain these things in the next lecture why this is coming, and I'll derive the formula as well. But here try to understand what COMSOLs are solving. COMSOL is solving only these two equations. Navier-Stokes equation, that is the force balance equation or momentum balance equation. And then second equation is the continuity equation. So once we get to know all of these things, we'll come to creating mesh. So since there are various mesh options available, extremely fine, all of these things. But I will be taking only coarse mesh because it will, take very less time to solve the problem. And why we are using mesh? Already I've described this in my previous lecture because COMSOL this software is based on the finite element method, and it will create mesh, and for all mesh it will assume that is a node, and that will solve the mathematics. That is a partial differential equation. And then we'll go to build all. So it will create mesh. So you can see that if we use coarse mesh, then the mesh will getting generated very fast or quickly. But if you use fine, extra fine, then that will take some time. So now the mesh got created. Now we'll go to stationary, and then we'll go to the compute. So once we do compute, then it will start solving the finite element method, partial differential equation using finite element method. And it will take some time because you can see 91,000 domains are there, 9256 boundary elements are there, 396 edges elements are there. So lots of components are there for the problem. So definitely it will take some time, but let's wait for some time why it solves. And then we'll go for the velocity profile, and because we are solving this for Newtonian fluid for the laminar flow condition, and we are expecting that velocity profile should come parabolic. So let's see how it comes. So just 1 second. It will take only 2 to 5 seconds now, and the problem will get solved. Okay, so now you can see that it solved the problem, and this shows the velocity, right? So if you zoom in these things, so you can see it made a five slice, something like that. So I'll show you this. This is a slice kind of thing. So what happens at boundary? It was no slip boundary. Sorry, at the wall it was no slip boundary condition. So velocity should be zero, and in the middle velocity should be maximum because the profile of velocity inside the circular pipe is parabolic. So you can see here. First, I'll start with this. Okay, so it should be visible because now if you can see this part here, the velocity profile is looking a bit parabolic, and finally we are going near this slice is near the wall, right? So velocity is approximately, you can see it's very less, approximately zero, but in the middle velocity is high, right? But you can see the blue region is the lowest velocity, but in the middle you can see there is a more greenish kind of thing, and that shows higher velocity. So this clearly indicates you that at center velocity is maximum, and at wall velocity is zero. But again, we are going from top to bottom. So if we go like that, see, this is just near the wall. Velocity is almost zero. And in at the inlet condition, you can see there is a parabolic velocity profile, and velocity profile will start evolving. And what happens now, once we go towards the center of the pipe, you can see the at velocity becomes maximum at the center. So let's say I'll make a slice one. So for one slice, you can see this looks complete parabolic profile, something like that. And near the wall, you can see there is a blue region that is called where the velocity will be zero, and it is validating that there is no slip boundary condition. And at the center of the pipe, you can see there is a maximum velocity. Is that clear? So now this is just a surface kind of plot. So we'll do line plot. So I'll go to result and then click on 3D plot group. So once we click on 3D plot group, then what happens? Okay, and now again we'll come to the 3D plot group, and then we'll click over. Sorry, we'll go to the data set, and then we'll go to cut line 3D. Right. So from cut line 3D, we'll go to a point. So since we want to calculate the velocity along and variation along the radial direction. So y and z will be 0. X should vary. So this is your x. So x will vary from obviously minus 0.05, and it goes to 0.05. So then we'll do plotting. So now you can see if you do plot here, okay. I think I'll make x is 0 and y is minus 0.05 and y to 0.05. So once we do, now you can see that this, once you plot these things, it shows the radial variations of the line. This line shows the radial variations. So now we want to calculate, or you want to plot the velocity along this line. Okay, so in order to plot this along this line, we'll go to again. Just 1 second. Okay, once we get, then we go to line 3D over there. Just 1 sec. So yeah, this was cut line 3D, and so here I'll go to cut line 3D. Okay, and then I'll plot. Oh, sorry. We already defined cut line 3D, right? Searching for that. We see cut line 3D. Yeah. So it was 0. Then it was minus 0.05. Here it is 0.05. So then we define this cut line 3D. Then we'll go to results. As I have told you, sorry, I forgot to I was not getting this thing. So once we define the cut line 3D, so already we have cut line 3D one, right? And after that, again, we'll go to results. We'll do 1D plot group. And in 1D plot group, we'll go for cut line 3D. So once we do these things, cut line 3D, then we'll do plot. Okay. And then we'll go to the line graph. So here you have to select cut line 3D one because that was what our cut line 3D. And then I'll go to 1D plot group 4 and we'll click right and go to the line graph. Once we go to line graph, then here you can see there is spif.u. That is the velocity. So you don't have to change. So we want velocity profile. That's why we'll do this. Right. So since right now you can see this velocity profile looks like that. So there may be some issue in the velocity. So let's try to change the parameter. So once we change the parameter velocity, let's say 0.01, then we'll go to stationary, then we'll again run. Let's try to run this. So again, it will compute and hopefully here now you will get a velocity profile. So I just took the arbitrary velocity, arbitrary velocity, but again, the velocity should be, defined in that way so that it should be in the laminar flow condition, then only it will give you the parabolic profile. So I think in earlier case, when we use 0.01 meter per second velocity, it goes beyond the laminar flow condition in that particular length and diameter. That's why velocity profile was coming flat, but now hopefully here you will get a parabolic velocity profile. So let's check here. Yeah, it looks more parabolic, so I'll plot these things again. uh, it- why it is happening. Line graph on from cut line 3D. This is there. Cut line 3D was this is our cut line 3D and cut line 3D1. So we have to select cut line 3D1, then we have to go to line graph. And uh, okay, we plot. There is some issue here because in parameter 0.5, 0.01, let's try to make it 0.01. And water, fluid properties, all of these things are there. We have entered U node. Then we go to run. We compute this. Wait for some times. The calculation is running. So, sorry, the simulation is running. So we have to wait for some time. Yeah, so you can clearly see the velocity profile looks like that in this region. Why it is not coming mean velocity in the magnet profile. Okay, there is some issue in line plot. I'll discuss this things in later on. There would be some issue with the software. Okay, so I'll stop this lecture here. See you in the next.